let's have a look now. We spoke about this concept of resistors, okay? We said we've got a resistor. A resistor. And we show it like that, okay? Now, let's have a look. First of all, factors that influence resistance. Right, well, now let's think. Think of a hose pipe, all right? If you've got a pipe that size, this big fat pipe going down there, okay? A large diameter pipe, right? What does it mean? It means lots of water can go down it. Now let's look at a straw, okay? No, we've got a totally different situation. So obviously, one of the factors is going to be cross-sectional area, right? The cross-sectional area is going to affect resistance. Why? It's logical. If you look at it, the thicker it is, the more can go. The thinner, the less. We spoke about it earlier when we spoke about this tube here going down to this tiny little wire over there. So you've got all of this going, all of a sudden it's going through the little one. What happens? We get heat given off over here, right? So the cross-sectional area is a factor that influences the resistance. 2 is obviously the length. Right? The longer it is, the more resistance there's going to be, right? It's basically the same thing as the longer the swim, the more the resistance, because you're battling against the water for a longer period of time. So the length plays a role. The length is the longer, the greater the resistance. So the longer, the more resistance. Okay? 3, okay? We've said the next one is the temperature. Okay? Right? Now let's say we've got it hot and cold. Hot, high resistance. Why? Why? Well, it's like this. The hotter it is, what happens when we apply heat? Okay? Let's have a look. We apply heat. Okay? Apply heat. Okay? What is heat? Heat is a measure of the kinetic energy of the individual atoms. And we say that is a half mv squared. Correct? So heat is a half mv squared. Therefore, we are now heating up. Therefore, the electrons inside the metal, the electrons here, remember they're a delocalized cloud, remember from chemistry. So what happens is these guys start vibrating more and more, and they then impede the flow of these electrons. This electron here wants to get out that side, right? That's his path. But he's being knocked by these other electrons that are going this way and this way. So it's impeding his flow, right? Because the energy of the electrons inside the metal is, or the conductor, is now higher. So they are banging against this. This electron wants to come this way. It's coming here and he's being banged off course, right? These guys are bouncing around faster and faster, so it bangs this electron off course. This, obviously, the contrary must be true. If you cool it down, okay, it means this electron and this electron basically almost still. The colder, then it means this guy can come along and he can get a straight path. Whereas here, he's being bounced like this, okay, until he gets out. Over here, he's got a straight path, which means the resistance to flow is less, okay? Some superconductors are cooled right down to very low temperatures and the current flows with virtually no resistance, all right? Apparently, you can induce a current in one of those loops at a very cold temperature and it'll keep flowing forever, basically, our lifetimes, okay? Now, then obviously, the last thing that we've got to talk about resistance is going to be the type of material, right? Why? Well, obviously, metals, okay, are conductors, right? Wood is a non-conductor. Non-conductor, okay? That really I should rewrite, but it's a non-conductor, all right? Non-conductor. Yeah. I should probably go for actually printing lessons. Write it non-conductor. That's better, much better. It's a conductor is a metal and a wood is a non-conductor. Paper is non-conductors, right? Well, obviously the type of material that we're going to use will tell us. A non-conductor, the resistance is high. In fact, it's infinitely high because no current goes through. So metals are conductors, their resistances are lower, all right? Well, you get something like this. Different metals have a different slope. We'll see in a few minutes that the slope of that line is in fact a measurement of resistance. Okay, now let's just create another one. And okay, so, and as we've said before, we measure it in ohms. Okay, now let's have a look at this. Let's start the functionality side. Now we can do this, can't we? We can have resistors like that, or we could have resistors like this. Right? And those in between are my wires, that's all, right? These are called series. Remember that term? Where we had cells one behind the other, series. These once again are the other one is parallel. Okay? This is parallel. These are in series. Now, if this one is measured as R1, this one is R2, this one is R3. Okay? We're going to do examples using these. We want to know what is the total resistance. I will explain to you why in a few seconds. Total resistance, R, okay? Total resistance or effective resistance. I prefer that one. Effective resistance, R effective, is R1 plus R2 plus R3. Remember batteries, cells, we added them together. Here we add them together. Okay? So if that's 1, 2, 1, 5, and 10, it's 16 is the total. We just add them together. All right? To work out, but what have we actually done? What we've done is we've worked out what I call the ghost resistor. Okay? We've worked out one resistor to replace them all. All right? And if you've read Tolkien's book, jeepers, it's gone out of my mind now, Lord of the Rings, one ring to get them all. This is basically one resistor this is our effective here. What it means is we work out the total of all the resistances there and we replace it with one resistor. Okay? That's what we're doing. Let's have a look at this as parallel. Here we've got R1, R2, and R3. What is happening here? What's happening here is there's a formula for it. We say 1 over R effective is 1 over R1 plus 1 over R2 plus 1 over R3. Okay? In other words, we put them 1 over, add them, and remember, at the end, when we've worked that out, we have to invert. Okay? Don't forget to invert at the end. In other words, turn it upside down to get R effective. Okay? Now, let's have a look at this. Okay? I want to just do a little bit more on that circuit there of these two here. Okay? I want to draw this one again. Okay. Okay, like this and like that. Okay. Here's my R1, R2, R3. The first thing we ever do in circuits is we put in the current. Okay. So I'm going to put in I over here. Now can you see the electrons flow right through R1, and the same electrons flow through R2, and the same electrons flow through R3, which means the current through each one is the same. This is a very important concept, okay? This current flows through the same. So we say the current is the same through parallel resistors. Okay? Very important. This circuit over here is called a voltage splitter. All right? This here is called a voltage splitter. Okay? We'll get into that in a while. But I just want you to know that, or look at it and say, right, if I've got a current coming and there's a resistor, it must all flow through that, and it all goes, and the same current goes through each one. Now, what happens if we've got a parallel connector, parallel resistors? Let me just bring it down a bit. All right. We've got resistors that are in parallel like this. Okay. You may be asking why. Well, what's the purpose? Well, these all do different things, right? When you put them together, they do different functions inside a circuit. Okay. Resistors basically govern the current flow, etc., in a circuit. Now let's call this R1, R2, R3. Remember the formula, the 1 over R effective. Let's just go back to it. Okay, let's just go back. There it is. It's in parallel. This formula here, 1 over R is that. Okay, and that would lead us to putting in I forgot to put in my ghost resistor, is basically going to replace all of those with R effective there. Okay, now let's go back over here. Right, now let's put in the current. The current I comes here. Okay, now think of it like this. Think of water flowing, right? Right. Water flows, there's a channel, water's flowing through. Now we have a thing in the channel that looks like that. Okay. Let's look which way the water's going to go. Here comes our flow of water. The water is going to mainly go that way, isn't it? Most of it, some is going to go around there, but most water goes that way. This is the path of least resistance. So obviously the water is going to split flow, right? You've seen it in rivers, in the street, etc. The water is going to go where there's least resistance, all right? Well, guess what? An electric current, yep, does exactly the same. It is going to split over here. Some electrons are going to go up, so we call that I1. Some electrons are going to go through and some are going to come down. So the current, and we always do this in a circuit, when we first get the problem, we put in the current and we put it through all the components like that. That's critical because it'll focus your eye on where you need to solve something. There's only 3 things in a circuit: resistance, voltage, and current. That's all we're going to deal with. We're not going to deal with any others. Okay? So what happens here is we've got, look what's happened. What can I call this? This is a current splitter. So whenever we see resistors in parallel, we think that it's obviously the most electrons are going to go through the least resistance, right? The most current will flow through the least resistance. Okay? That's pretty obvious, isn't it? It's going to go through the least resistance. Okay? Right. Now, let's just do, just add another page. Let us do an example over here, right? Let us say that we've got a 5 ohm and a 3 ohm. Okay? We've got a 5 and a 3 ohm over here. A 5 ohm and a 3 ohm. Right? And they ask, what is the effective resistance or the total resistance here? They are in series. Therefore, R effective is R1 plus R2, which is 5 plus 3, which is going to be 8 ohms. Let's now say we put them like this into a current splitter. All right, and let's call that the 5 ohm there. Let's just be a bit tidier. Whoops. 5 ohms and 3 ohms here. We say 1 over R effective is going to be equal to 1 over 5 plus 1 over 3, which is going to be 15. That's going to be 3 plus 5, which is going to be 8 over 15. Therefore, now remember, invert. This is where most of the errors occur. People forget to invert. So 1 over R effective is 8 over 15. Therefore, R effective is equal to 15 over 8 ohms. Almost 2. All right. What have we done? We have effectively put in my pretend or ghost resistor. 15 over 8 ohms is that one. Over here, I have going to now replace that with an 8 ohm resistor over there. Okay. Moving along. Okay. Let us do a slightly different one. Okay. Let's do this one. Here we've got a circuit that looks like this. Okay. Let me just try and make it a bit neater. Okay, we've got a whole bunch of resistors, a 6 ohm and a 12 ohm. Over here, a 4 ohm and a 2 ohm. What did I say? What is the first thing you put in? The first thing we put in is we put in the current flow. So we say, right, I comes this way, and it splits to I1, and it splits to I2, like so. Okay? Now, next we say, right, this current is going to go through here, isn't it? That's also I2. That is I1 over there. It's going to go through because we put the current with each component. That's important. Now, the next phase is we say to ourselves, right, hold on. We've at the top, we've got current going that way. So this here, I need to find my effective resistor for the top. They are in series, which means what? I must add them together. So here, my R effective is 12 plus 6 is 18 ohms. All right? So now I have made the circuit smaller. I have now got a circuit. Okay, hold on. Let's just do it this way. What have we got? We've now got a circuit that looks like this, correct? We've got that. And we can say that is 18 ohms over there. And this over here is going to be, on that side, we're going to have 6 ohms over there, like so. Now I've got an 18 and a 6 in parallel. I've got to do a further reduction on it because this is my 6 ohm over here. This is a 6 ohm resistor here now. the effective. I've got to do a further reduction to find out what that guy would be. Now I've got the guys in parallel, so I say 1 over R effective is 1 over 18 plus 1 over 6. That's 18, and that's 1. 6 is 3, which is 4 over 18. And what mustn't I forget to do? R effective is going to be equal to 18 over 4. So I make that 18 over 4 ohms. That is my resistor. Essentially, we've broken all of those down. Okay? We've broken them all down. That's 4.5, by the way. Let me just put that. Becomes 4.5 ohms. We've broken it down from a complex structure to a simple form, right? The next step, what we're going to do is we're going to look at putting them into a circuit and then working out voltage, current, etc., etc. Okay? That's the next one that we're going to go through. So what we've done now is we've done resistors in factors that affect it. We've done resistors that are in series, in other words, one behind each other. Resistors in parallel, which are split like cells were, right? One above the other. We've done one where we've got them in series and parallel. Remember, you just break them down, but put the current in first. You'll see that in the series now. Thanks for watching that. I'll see you in the next one, and we'll do some circuits. In fact, we'll do quite a few circuits, okay? Because this is a key part to this year and next year and grade 12. Thanks.